Hello everyone, welcome back to Applied Engineering channel. Today we are diving into part 4 of our Cycle DHX series and we are focusing on two-stage compression with intercooling. If you are new here, smash that subscribe button and hit the bell icon so you don't miss any of our HVAC deep dives. Today we are exploring how this process works, its advantages, applications, and the refrigerants dominating the industry. Plus, we will use NIST Cycle DHX software to compare their performance. So let's jump in it. First, let's break down what's two-stage compression with intercooling. Imagine you are compressing a gas like a refrigerant to a high pressure. Doing it in one go takes a lot of energy and heats up the gas. That's where two-stage compression comes in. The gas is compressed in two steps with an intercooler between to cool it down. This reduces the work needed for the second stage and boosts the overall efficiency of the system. So this setup is a game changer for systems needing high pressure or low temperatures like industrial refrigeration or cryogenics. So stick around because we will see how it performs with different refrigerants using cycle DHX. So why we use two-stage compression with intercooling? So here are the key advantages. Number one, the increased efficiency. Cooling the gas between the stages means less energy is needed to hit the target pressure and cutting the power costs. Enhanced durability. Lower temperature reduce wear on the compressor parts like pistons and valves so your system lasts longer. Higher pressure capabilities. Two-stage handle higher pressures than single-stage systems and perfect for demanding applications. Continuous operation. So these compressors are built for heavy-duty non-stop use like powering multiple tools at once. Versatility. From sandblasting to precision cooling, they handle a wide range of tasks. So these are the benefits that make the two-stage system more efficient and reliable as compared to the single-stage system. The applications of two-stage systems. So two-stage system shines when there is a big pressure difference between the evaporator and the condenser. So here where you will find it. Low temperature refrigeration. Just think of the cold storage warehouses, frozen food plants, or fish and meat processing plants. Industrial refrigeration. Systems needing evaporator temperature as low as minus 40 degrees Celsius to minus 80 degrees Celsius like chemical plants. Gas liquefaction. It is used for ammonia, CO2 or even liquefied natural gas LNG for gas liquefaction process. Cryogenics. Used for the ultra low temperatures where multiple compression stages are required. Large scale HV and AC. It's less common now but still used for the extreme temperature lifts in big buildings. So now let's dive into the refrigerants powering these systems. Regulations like Kigali Amendment are pushing low GWP options. So here what's trending. Ammonia, the king of industrial systems, it's low cost, super efficient, with zero GWP and no ozone depletion potential. You will find it in food storage and ice plants. CO2, it's gaining traction in supermarkets and transcritical systems. It is natural, safe, and works great with intercooling setups like parallel compression. Hydrocarbons. R290, R600A, R170, that is propane, butane, and ethane used for the ultra low temperatures like LNG liquefaction. They are efficient but require careful handling due to flammability. HFO and blends. R1234YF, R1234ZE, and R513A. These low GWP options are popping up in large chillers, improving efficiency in staged systems. So each refrigerant has its strengths, but how do they stack up in the performance? So let's see in the cycle DHX. So now we will move towards our simulation software, that is cycle DHX. So we will open cycle DHX version 2.0. First we will go to file and we will open. Here we are going to open the examples files which are already provided by cycle DHX simulation software. In the example at the bottom you will see refrigeration intercooling example with R32. Just click it and open it. This will load the file data, and here you can see it has already selected refrigerant R32. For the cycle option, it has selected the two-stage compression with intercooling, and here you can see its diagram. An important thing is that you have to define the intermediate pressure, which is already defined as 13 bar or 1300 kilopascal. This intermediate pressure is very important parameter for the two-stage compression with intercooling, because sometimes we modify it or we vary it to check at which point we have maximum COP. So this is what we will also study in this video. In the cycle option you can see it is already selected the impose mode and delta T mode. First we will check for the reference parameter and we will run it into the impose mode so that it will impose all the geometry parameters. Here we can see that the system cooling capacity is 12 kilowatt, and we can see that the vapor line's pressure drops are also assumed 0. Also the auxiliary power is assumed 0. And both compressors, they have the isentropic, volumetric and electric efficiency of 100%. So now we will run it into the impose mode first. Here you can see it has run it in the impose mode. Now we will move towards the simulate mode. In the impose mode it has saved some reference parameters which it will use for our simulations. And now in the simulation you can see some of the boxes are grayed out which we cannot change. So now we will just run it into the simulate mode. So here you can see it has run it into the simulate mode. Now what we can see, it has calculated the thermodynamic cycle results at all the state points, and it has calculated the compressor and system results. The important one are the compressor power and the COP cooling and COP heating values, and also compressor suction volumetric flow rate values. And here we can see the heat exchanger results also. So what we will do, we will just see what are the COP values, or can we improve these values or not. For example, here we can see the COP of cooling is 4.661 and COP of heating is 5.661. Now we have to see that how we can improve these COP values. For this we will go and check the TS and pH diagrams. So for those diagrams you will just click on the TS and it will open the TS diagram, and then pH, it will open the pH diagram. So here in this TS and pH diagram you can see clearly that it has equally divided the pressure levels and the temperature levels in the two stages. So it should be the most efficient intermediate pressure points and temperature points. But let's see, while changing these pressure levels, how it affects the COP of the system. So what we will do, so we will just save the results of R32. We will name them R32 two-stage. Now what we will do, we will go back to the cycle options, and here we can see that the intermediate pressure is 13 bar or 1300 kilopascal. Now what we will do, we will just reduce it to 10 bar or 1000 kilopascal, and we will see how it affects our results. We will go back to cycle specification and then we will run this simulation again. Now here we can see the latest results. What we will do, we will also save this file so that we can compare it with the previous results. We will save it R32 10 bar. Now we will just open and compare these results. So here you can see when we run it at 13 bar, what we get the COP cooling of 4.661 and COP heating of 5.661. When we change the pressure to 10 bar and then we run the simulation again, then the COP of cooling is 4.677 and COP heating is 5.677. So you can say that the COP of cooling and COP of heating has improved by decreasing the intermediate pressure. So this is how we use the two-stage intercooling compression cycle, and usually what we do, we vary this pressure level to get the maximum COP of the system. Here you can see that when running it to 10 bar pressure, it has not divided the two stages equally. We can see that the temperature levels and the pressure levels are not equally divided. This means that on the second stage of the compressor, there is more load as compared to the first stage of the compressor, which is not a desirable fact. So this is how we have to do optimization between the optimum intermediate pressure and COP of the system. What you can do further is that you can also use it for different refrigerants. So what you will do, you will go back to the refrigerant, you will go to single compound fluid and you will select propane. In the cycle options, you will change the pressure level back to the 13 bar or 1300 kilopascal, and then you will run the simulation. In this case, you will get the results for the propane. And for the propane, we can see the COP values. COP cooling is 4.5 and COP heating is 5.5. So as compared to the COP values of R32, we can see that the propane values are lesser than the R32 values. You can also see its TS and pH diagram. And from this diagram, we can learn that the two stages are not equally divided. That is why the propane is not giving us a better COP value. So to improve its efficiency, what we will do, we will further decrease down the intermediate pressure so that it will equally divide the pressures in the two stages, and it will improve the efficiency of the system. So let's go and to the cycle option and decrease the pressure. Instead of 10 bar, this time I think we should go for 6 bar, and now we will run it again. So here you can see now it's a little bit, you can see, divided pressure, but still it needs some amendments. So this is how you can just play with this software and you can get different amazing results. So that's it for this video. If you like this video, Please like it and subscribe my channel. This is the only way for motivating me for making more such type of videos. Thank you.